Okay, so now that you're comfortable with finding solutions to a differential equation centered around an ordinary point, we then start to look at singular points. So we have looked at these second order differential equations and saw that when x equals x sub 0 is an ordinary point, we can come up with a power series solution. Not only one, but remember that theorem we looked at said that we could get two. We were guaranteed to get two solutions as long as our power series was centered around an ordinary point. So now what we want to do is say, well, what if x equals x sub 0 is a singular point? Can we still come up with a power series solution to the differential equation if we're centered at a singular point? And the answer turns out that, yeah, I actually can, but we just got to change the form. So the power series that's going to solve the differential equation centered at a singular point is going to look like this. And if you notice, the big difference is right here. N plus r instead of n, where r is just going to be some constant that we're going to need to find. Now that throws a little wrinkle into this whole thing that we didn't have to deal with before, but that's because we're working with singular points and centering our power series at singular points instead of ordinary points. But if you've gotten comfortable with finding solutions centered at ordinary points, adding this little wrinkle really shouldn't be that much of an issue for you. So we're going to have to define singular points into two categories, regular and irregular. So first, let's look at the definition here. When we're working with a standard form second order, which we've done this many times before. This is our standard form second order. We can define x sub 0 as a regular singular point if x minus x sub 0 times p of x and x minus x sub 0 squared times q of x are both analytic. Now analytic means can be written as a power series. Okay, that's what we've talked about before. Now if something's not a regular singular point, then we call it an irregular singular point. Now remember, p of x and q of x are not going to just be some random functions, because we're specifically only going to look at polynomial coefficient differential equations. So a1, a2, a0, they're going to be polynomials. And let's assume that they have no common factors. Okay? And we're looking at a sub 2 of x to be 0 for a particular x. Okay? Because that's when we would know we would have a singular point, right? We've talked about really determining if we have a singular point is all about a sub 2 being equal to 0. So then when we form p of x and we form q of x, since a1, a2, and a0 are polynomials, then p of x and q of x would be these rational functions here, polynomial divided by polynomial. Okay, so p of x would be this one, q of x would be this one. Okay, and we would reduce those to their lowest terms, again, based off of factors. So what we could say is that if x minus x sub 0 only appears at most to the first power in the denominator of p of x and at most to the second power in the denominator of q of x, then x equals x sub 0 is a regular singular point. Because if the reason for this is if x minus x sub 0 appears at most to the first power in the denominator of p of x, then we can go up to here and say, well, x minus x sub 0 times p of x would be analytic. Why? Because if you think about it, if p of x, let me find something you can see. So if p of x has x minus x sub 0 at most to the first power in the denominator, and whatever's in the numerator, it would just be whatever a sub 1 was. But let's say it has x minus x sub 0 at most to the first power, then when I multiply by x minus x sub 0 times p of x, so in this case on both sides, I would be able to cancel this out of the denominator, and therefore the rational function that would be left over here wouldn't have that as a 0. X sub 0 wouldn't be a 0 of the function. Therefore, this whole thing would exist and therefore be analytic. And the same thing goes for x minus x sub 0 squared in q of x. I think the best thing for us to do would be to see examples to clear this up. So here are a couple examples. So let's look at A. If we look at A, we could say p of x is going to be 3 times x minus 2 over x squared minus 4. And q of x would be 5 over x squared minus 4. Now we could simplify this into 3 over x plus 2, because the x minus 2 from this being factored would cancel. And this is simply just going to be 5 over x plus 2, x minus 2. Now, when the leading coefficient, this a sub 2 here, is equal to 0, we have singular points. So we have singular points at x equals 2 and x equals negative 2. Now the question is, are they regular or irregular singular points? Well, does x minus 2 appear, I should say does, x minus 2 appear at most once in p of x and at most twice in q of x. Well, it doesn't appear at all in p of x, so yeah, I guess that would be checked off. And it only has it once in q of x, so it's at most twice. Yeah, so it checks off there. Because if I took x minus 2, well, let me change the color. If I took x minus 2 and I multiply that by p of x, would 2, which is where this came from, still be a value for which p of x is undefined? Would it be what we call a singularity? A singularity is where the function, the rational function, doesn't exist. And if I multiply p of x by x minus 2, since there's not even a factor there, well, then we're good. And if I multiply q of x by x minus 2 squared, we would also be okay, because it would remove the singularity out of there. So 2 would be regular. Now let's look at minus 2. So x minus this, which would be x plus 2, one time in p of x, 2 times q of x. Now this is at most one time, at most 2 times. So if I multiply p of x by x plus 2, does it remove the singularity? If I multiply q of x by x plus 2 squared, does it remove the singularity? Well, again, if I multiply this by x plus 2, it would remove that factor in the denominator. If I multiply this by x plus 2 squared, it would remove that denominator and therefore remove the singularity. So this would also be regular. Let me just give you a hypothetical here. Okay? Let's erase all this. So the hypothetical is, let's just say we're looking at 2. So then we're looking at x minus 2 to be multiplied by p of x and q of x. And let's say p of x was 5 over x minus 2. And let's say q of x, though, was 3x over x minus 2 to the third. So if I multiply p of x by x minus 2, would it remove the singularity, the place where 2 makes the denominator 0? Well, yeah, if I multiply p of x by x minus 2, it'll cancel with that denominator. Now, if I multiply q of x by x minus 2 squared, would it remove that singularity? And the answer is no, because this x minus 2 would cancel with 2 of these, but I'd still have 1 left over. So 2 would still make this denominator 0, and therefore wouldn't remove the singularity, and therefore q of x wouldn't be analytic. So in this case, 2 would then be a irregular singular point for some hypothetical scenario like this. I don't think we need to do a ton of work to see whether or not we have regular or irregular singular points. I think we could look at it and say, all right, I can see what would happen if I divided through by my a sub 2. I can see that my denominator would continue to be 0 even if I multiplied by the x minus each one. So let's look at this example here. B. First off, the numerator, this thing which will be turned into the denominator of the p of x and q of x, that equals 0 when x equals 0 and when x equals negative 1. So those are your singular points. Now p of x would be x squared minus 1 over x squared times x plus 1 squared. And q of x would be 2 over x squared times x plus 1 squared. So the factor here would be x minus 0, and the factor here would be x plus 1. So I got to multiply p of x by x minus 0, or really that would just be x, okay? And multiply q of x by x minus 0 squared. Would it remove the singularity in either case? And the answer would be no, because if I multiply p of x by just x minus 0, which is x, I would cancel this x and this x, but I'd still be left with an extra x down here because there's squared. Now, if x was 0, it would still make this denominator 0 even if I multiplied by that. And therefore, this would still be a singularity of this fraction. P of x would not be analytic, and therefore this would be an irregular singular point. I don't even have to look at q of x once that p of x one doesn't work. Now how about x plus 1? Well, look, I can actually simplify p of x. This is going to be x plus 1 times x minus 1, and I can cancel one of these x plus 1s. So actually, if I multiply this one by x plus 1 and this one by x plus 1 squared, does it remove the singularity? Well, x plus 1 times this, yeah, it would remove the singularity. X plus 1 squared times this, yeah, it would remove the singularity. So that tells me that negative 1 would be regular. So this one is irregular, and this one is regular. So hopefully you get the hang of this. So if we go one more, let's look at this one. Clearly you see that we got plus and minus 1 would be your singular points. Divide here, divide here. X plus 1 would only appear in this denominator when I divided one time. It would only appear in this denominator one time. So it would be at most once here and at most twice here. It would fulfill that category. So that would be a regular singular point, and the other one, negative 1, would work the same way. So plus and minus 1 would both be regular singular points. The reason why we need regular singular points is because of Frobenius' theorem. This is the same theorem generally we had before that told us we were guaranteed to get 2 solutions. But in this case now it's talking about singular points. So what it says is if x equals x sub 0 is a regular singular point, so that's the key, it's got to be regular, then there exists at least one solution. Doesn't say we're guaranteed to get two, but we are at least guaranteed to get at least one solution of the form x minus x sub 0 times to the r times this power series. Well, if you're multiplying the power series by x minus x sub 0 to the r, this is actually what you're going to have, because here you have x minus x sub 0 to the n, and here you have it to the r. So if you're multiplying them together, it's to the n plus r, where r is some constant that we're going to have to determine, and the series will converge at least in some interval x minus x sub 0 is less than capital R. This is just saying that you have an interval convergence. Okay. So the trick to getting through this whole thing is we need to find r. What r ends up being is really going to help determine whether or not we have one solution or two solutions, but we're saying at least one solution. So we'll look at a couple of different examples. I'm going to start explaining a little bit about how r affects the answer. But overall, we're going to use the same setup that we've used for the ordinary points in terms of how we make our way through these problems. All right, a couple of things wrong on this slide I'm going to fix first. One is this exponent there. Two is this equation should be 3xy double prime plus y prime minus y equals 0. We're going to solve this differential equation. All right, so first off, let's look at x equals 0. X equals 0 is a regular singular point. It makes the leading coefficient 0, so it's singular. And then when I divide 3x by p and q, it's going to, or into forming p and q. That's only going to appear in the denominator of p once and q once, so it fulfills the regular singular point. So that tells me that I should be able to find at least one solution centered at 0 for the differential equation. Okay? Now that solution has to be of this form though. Remember, this is centered at 0, but the power can't just be x to the n now. It has to be x to the n plus r. So I can find a power series centered at 0, which is what this is, as long as that power series is of the form c sub n x to the n plus r, where r is going to be some constant we're going to have to find out. All right, so if that's the solution, then what I have to do is I have to plug that into the differential equation and find out what the solution would actually have to be. Well, that means I'm going to take the derivative of y, so find y prime, and find the second derivative of y. Now, if I find the derivative, it really doesn't work a whole lot differently than before. I'm going to use the power rule. This power is going to have to come out to the front. So you got n plus r. The new power is 1 less. But the major difference here is that the index is not bumping up by 1. I'll explain that in a second. Then we're going to go to second derivative. Now this power is going to come out. So n plus r minus 1. The new power is 1 less again. So now it's n plus r minus 2. Again, index didn't bump up by 1. So why is the index not bumping up by 1? Well, because if y equals this, if I wrote it out, when n equals 0, I would get c sub 0 x to the 0 plus r, which would be x to the r. Then I get c sub 1 x to the 1 plus r. Then c sub 2 x to the 2 plus r. C sub 3 x to the 3 plus r, etc. And I took the derivative of that. Well, because this isn't actually a constant anymore because of the r, it's actually just x to the r. The derivative would be r c sub 0 x to the r minus 1. And the next one would be 1 plus r c sub 1 x to the r, because it would be plus 1 minus 1. And then I keep going and going and going. But either way, the first term isn't going to go away because this first term is not a constant. So then this term right here is not going to be 0. So we're not losing the first term like we were before. So since we don't lose the first term, there's still a c sub 0 term there after we take the derivative. I keep the index at 0 every time I do the derivative. That's probably one of the biggest computational errors people will make with these singular point questions, is that their derivatives are not going to be correct because their index is not correct. We do not bump the index up by 1 when we're centered at a singular point. It stays at 0 the whole time. All right, but now it's time to plug in y double prime, y prime, and y into the differential equation. So we'll have 3x times the sum of n equals 0 to infinity of n plus r minus 1, c sub n, x to the n plus r minus 2, plus the derivative, which is n equals 0 to infinity of n plus r, c sub n, x to the n plus r minus 1, minus the original y, which is n equals 0 to infinity of c sub n, x to the n plus r, and that equals 0. This is still a homogeneous equation. So next thing I'm going to do is very similar to what we do before. We'd have to push this 3x into the series. So this is going to become the sum of n equals 0 to infinity of 3 times n plus r times n plus r minus 1, c sub n, x to the n plus r minus 1. Because this is an x to the first, this is an n plus r minus 2, so now it's n plus r minus 1. All the rest of these series are going to stay the same. C sub n, x to the n plus r minus 1. And this is going to be the sum of n equals 0 to infinity, c sub n, x to the n plus r. Okay? So next thing I'm going to do is I'm going to deal with this x to the n plus r minus 1, n plus r minus 2, whatever it is. So if you look at each one of these, I could write this as x to the n minus 1 times x to the r. Because if I multiply these bases, I should add the exponents. And this will be x to the same thing, n minus 1 times x to the r. And this will be x to the n times x to the r. So technically, each one of these has an x to the r in them. And r is just some constant, so that's not going to change as n goes from 0 to 1 to 2 to 3 to 4. So I could factor this x to the r outside of this series, this x to the r outside of this series, and this x to the r outside of this series. And if they all have an x to the r outside of them, I can factor it out of the whole thing. And I can look at it like this. So I have the sum, I have another sum, I have another sum. Okay? And so what happens here is I have two things multiplied together equal to 0. Either this equals 0 or this equals 0. And we've talked about this before. If this equals 0, then x has to equal 0. If x has to equal 0, then that essentially tells me y equals 0 is the solution. But again, since it's homogeneous, we would have known that that was the solution all along, so that tells us nothing. So what we could do is we could just drop that off and just look at now what we have. Ultimately, what that's doing is it's saying, okay, let's just get rid of this, this, and this. And now let's deal with it, which will basically be get rid of this, this, and this. Okay? To simplify what we're looking at here. So if I did that, let's get rid of all this that I just talked about without having to rewrite all this all over again. What we would get would be the sum of n equals 0 to infinity of 3 n plus r minus 1 c sub n x to the n minus 1 plus the sum of n equals 0 to infinity of n plus r c sub n x to the n minus 1 minus the sum of n equals 0 to infinity c sub n x to the n. Now take note at this step. This is something you're going to see happen with singular points more so than it did with ordinary points. Look at this and look at this. They both have the same exponent on the x, and they both have the same starting index. Those are the two requirements I need to put the two series together. So what I can do is I can put these two series together right now before I think about switching my powers over to k and making my indices match up. I can do this now to simplify some of the computation as I go. At this point, that's what you should be doing in these problems. Look to see if you can condense some of these series moving forward. If you don't, it's okay. It's not going to be the end of the world, but you would save yourself a lot of computation if you can condense some of this down. So I'm going to do that. So these two series right here are going to come together. They both start at 0. They both have an x to the n minus 1. And so then I just have this coefficient plus this coefficient. Well, notice they actually both have a c sub n in them, so I could pull that out. They both have an n plus r in them, so I could pull that out. And then say, okay, well, what would I have? I would have 3 times this plus, well, since I pulled all this stuff out, the only thing left sitting here is a 1. So I'd have 3n plus 3r minus 1, that's 3 times this, plus 1. And so that condensed those two back together as 1, and you notice this plus 1 minus 1 will cancel each other out. And I still have this series sitting here, which would be minus the sum of n equals 0 to infinity of c sub n x to the n. Besides these r's sitting here and here, this doesn't look that different than what we were dealing with the ordinary points. So now what we want to do is we want to condense this down into one series, but we can't because now our powers are not the same. So what we would do is we would have to let k equal n minus 1, let k equal n, and then we can go from there. Same process that we had before. In the last slide, I made a little mistake. I had this 3n plus 3r minus 1, and I really shouldn't have had that. It was really supposed to be the sum of 3n plus 3r minus 3 plus 1, because we had this n plus r minus 1 with a 3 on the outside, and that 3 should have distributed in to everything, so this should have been a 3, which then would make this piece right here 3n plus 3r minus 2 into this piece right here. So now we're at this point. Again, here's the 3n plus 3r minus 2. All right, so we let k equal n minus 1, so n equals k plus 1. That's based off of this, and here k equals n because of this exponent here. So we end up with the sum of k equals negative 1 to infinity of 3k plus 1 plus 3r minus 2 times k plus 1 plus r c sub k x to the k minus the sum of k equals 0 to infinity of c sub k x to the k. So we can mess around with this a little bit more. Here, this 3 will multiply in here. And we would get out of this 3k plus 3 and a minus 2 would give me 3k plus 3r plus 1. Okay? Now you notice that this right here starts at negative 1. This one here starts at 1. So we got to run one term out of here. The negative 1 term has to go in for k. So that would give me negative 3 plus 3r plus 1 times negative 1 plus 1 plus r, that's plugging k and negative 1 in here, c sub negative 1, sorry, this will be k plus 1, sorry, c sub 0, x to the negative 1. Again, this is k plus 1 because it was n is k plus 1. So anyway, that would be c sub 0, x to the negative 1. So that's the first term of this series here that needs to come out. So now the index here is going to start at 0. So now the index starts at 0. If I go to put those two summations together, k would start at 0. And we could take this coefficient here plus minus this coefficient here, x to the k. So what would that give us? That would give us 3k plus 3r plus 1 times k plus 1 plus r, c sub k plus 1 minus c sub k, x to the k, and that whole thing should equal 0. So now here comes the point where the fact that we look at this fact, the homogeneous, this has to equal 0, and this whole thing up here has to equal 0. That's the coefficient in front of x to the negative 1. Well, what is this really? This is really 3r minus 2 times r times c sub 0. We're saying that that has to equal 0, as well as this whole thing has to equal 0. So that's 3k plus 3r plus 1 times k plus 1 plus r, c sub k plus 1 minus c sub k, that has to equal 0. Well, here I have three things multiplied together equal to 0. So that means one of these have to equal 0. So if this equals 0, r would be 2/3. If this equals 0, r would be 0. And if this equals 0, c sub 0 would be 0. Now I'm going to tell you right now that does nothing to help us. And you'll see why in a second. So not all of these have to be 0, but at least one of them does. So let's just say these two are the case. This has to equal 0, or this could equal 0. And we're going to say that this one doesn't equal 0. Because if it does, we get nothing out of it. Now over here, if this equaled 0, we would be with c sub k plus 1 equals c sub k over 3k plus 3r plus 1 times k plus 1 plus r. And that's working with k's from 0, 1, 2, 3, etc. So this recurrence formula looks a lot like similar ones we've had before, but it's got an r in it. Now we told you there's going to be a time we're going to figure out what r is. Well, we just figured out what r is right here with this piece. And r could be two different things. So if r equals 0, we would get c sub k plus 1 equals c sub k times 3k plus 1 times k plus 1. That's plugging in r of 0 into here. And if r equals 2/3, then we'll get c sub k plus 1 equals c sub k over 3k plus 3 times 2/3 would be 2 plus 1 times k plus 1 plus 2/3. What you see though is that you get two different recurrence formulas, this one and this one, depending on which r's you have. So what we'll have to do is we'll have to run out this recurrence formula and see what happens, and we'll run out this recurrence formula and see what happens. And again, you'll then see why c sub 0 equaling 0 does not help. So if r equaled 0, we would be dealing with this formula. And so let's go with k equals 0. Because k should be 0, 1, 2, 3. We would get c sub 1 equals c sub 0 over 1 times 1. And if k equaled 1, we would get c sub 2 to be c sub 1 over, what would that be? It would be 4 times 2. Okay? But c sub 1 was this, so that would be c sub 0 over 2 times 4. And if k equaled 2, we would get c sub 3 to be c sub 2 over, what's that going to be, 7 times 3? But based off of c sub 2, that would be c sub 0 over 2 times 3 times 4 times 7. Now here's why the c sub 0 being 0 doesn't help. Every one of these is in terms of c sub 0. So if c sub 0 was 0, then this would be 0, this would be 0, this would be 0, and every term would just be 0. And basically we would end up with 0 plus 0 plus 0 plus 0, and that doesn't help at all. Because of course 0 plus 0 plus 0 plus 0 would equal 0, and that doesn't give us a power series solution. So this is why we don't want c sub 0 to be 0. But the other values that will tell us what r could be, those are helpful. So then remember, the solution was of the form y equals the sum of n equals 0 to infinity of c sub n x to the n plus r. Remember though, with r equal to 0 in this case, that gives us the sum of n equals 0 to infinity of c sub n x to the n. Again, r because r is 0. So what does that tell me? It tells me that I should get c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x to the third plus c sub 4x to the fourth, etc. Which doesn't look very different than what we've had before, because again, this looks a lot like the series we've had before, mainly because r is 0. So we would get c sub 0 to just stay c sub 0. We don't want it to be 0. C sub 1 would be c sub 0. C sub 2 would be c sub 0 over 2 times 4. C sub 3 would be c sub 0 over 2 times 3 times 4 times 7. And then we would get something else for c sub 4 in terms of c sub 0, etc. These all have a c sub 0 in them. So y could be equal to c sub 0 times 1 plus x plus 1 over 2 times 4x squared plus 1 over 2 times 3 times 4 times 7 x to the third, etc. And right there, there's your first solution. There's y1. But remember, we had another r value, an r of 2/3. And if r is 2/3, we got a different recurrence formula. So now we'll look at that one. So now we have the r of 2/3. Okay, r of 2/3 gives us this recurrence formula, but because of this fraction, it's going to be a little bit hard to plug in 0, 1, 2, 3, and have to keep adding fractions. So we're going to mess around with this a little bit, make it a little nicer for us. This would be 3k plus 3. This would be k plus 5/3. I could factor a 3 out of here and then multiply that 3 over into there. And that would give me ck plus 1 equals c sub k over k plus 1, because with the 3 factored out of here, we just have a k plus 1. Then if I take that 3 and multiply it into here, that would give me 3k plus 5. Now that's a much easier formula to plug 0, 1, 2, 3 in with no fractions. So k equals 0, we get c sub 1 to be c sub 0 over 1 times 5. K equals 1, we get c sub 2 to be c sub 1 over 2 times 8. Based off of c sub 1, that would be c sub 0 over 2 times 5 times 8. Then k equals 2, we get c sub 3 to be c sub 2 over 3 times 11. So that's actually going to be c sub 0 over 2 times 3 times 5 times 8 times 11. All right, so I think that's good enough. So remember, the solution was y equals the sum of n equals 0 to infinity of c sub n x to the n plus r. Now with r being 2/3, that would give us the sum of n equals 0 to infinity of c sub n x to the n plus 2/3, which you could also write as the sum of n equals 0 to infinity of c sub n x to the n times x to the 2/3. Now, since this piece right here doesn't have any n's in it, it's technically a constant multiple for this power series. So I can pull that all the way out to the front. So now I could say that the sum, or the solution I should say, is x to the 2/3 times the sum of n equals 0 to infinity of c sub n x to the n, which if we wrote that out would be x to the 2/3 times c sub 0 plus c sub 1x plus c sub 2x squared, etc. And what that would give me would be x to the 2/3 times c sub 0 plus c sub 1 was c sub 0 over 5 plus c sub 2 was c sub 0 over 2 times 5 times 8 plus c sub 3 was c sub 0 over 2 times 3 times 5 times 8 times 11, and that pattern would just continue. If I then factored out a c sub 0, I would have x to the 2/3 still times 1 plus 1/5 x plus 1 over 2 times 5 times 8 x squared plus 1 over 2 times 3 times 5 times 8 times 11 x cubed, etc. And the 2/3 included, but this whole thing is now another solution. That's a second power series. Now, Frobenius' theorem said we're going to get at least one. We actually end up getting two because of our second R value generated another power series. Now, this x to the 2/3 is part of that solution. I could distribute it in here to every single one of these terms if I wanted to, or I could leave it out. To me, it doesn't really matter. We're not going to write this back into summation notation anyway, so it's fine to leave it out. But there's your second power series solution to the original differential equation. Now that equation that helped us figure out what R should be, where R was 0 or 2/3, was based off of these two factors, and when that equaled 0, that's called the indicial equation. Okay? And those values, 2/3 and 0, are called the indicial roots. Okay? Or sometimes they're called the exponents of the singularity. We usually will call them the indicial roots. Okay? And so we use those to help generate two different versions of this recurrence formula, which then helps us generate two different solutions. Now, it's not always going to work out that way because the Frobenius theorem says we're going to get at least one solution. But we'll start to see what happens. One thing you want to notice is that R, in this case, being 0 and 2/3, the difference between them, if I were to subtract them, the difference between them is not an integer. Okay? That has some significance to it. We're not going to get so far into solutions about a singular point that we're going to look at all the possibilities, but this possibility is probably one of the, at least the easiest ones to get through when it comes to the singularities and finding a power series centered at a singular point. So you're going to see a lot more examples of those. All right, so here I'm going to find I should probably write some more directions here. Find a power series solution centered at 0. Centered at 0. Well, what would 0 be? If you look at this, 0 is going to be a singular point. And since 0 is going to be a singular point, we would only be able to do this if it's a regular singular point. Well, if we divide by 2x and 2x here and here, and we look at q of x and p of x, that 2x only occurs at most once in p of x and at most twice in q of x. It's actually just once in each case, but anyway, that makes 0 a regular singular point. So the solution should be of the form, y should be of the form n equals 0 to infinity of c sub n x to the n plus r. That's centered at 0, but we got to have the r because of the regular singular. And y prime would be the sum of n equals 0 to infinity of c sub n x to the, it should actually be c sub n times n plus r x to the n plus r minus 1, and y double prime should be the sum of n equals 0 to infinity of c sub n plus r minus 1, x to the n plus r minus 2. Plugging all that into each one of these places, we get 2x times the sum of n equals 0 to infinity of c sub n plus r minus 1, x to the n plus r minus 2, plus 1 plus x times the sum of n equals 0 to infinity c sub n plus r x to the n plus r minus 1, plus y, which is n equals 0 to infinity of c sub n x to the n plus r, and that should equal 0. So, and none of this is much different than a lot of the ones we did with the ordinaries except for all these r's. So we'll have to push this 2x in, we'll have to distribute this into here and here, okay, to get it inside the series. And ultimately that's going to give us the sum of n equals 0 to infinity of 2 c sub n plus r minus 1, x to the n plus r minus 1, because this x to the first and this x to this n plus r minus 2 gives me minus 1. Then this distributed in here and here is going to give me First times the 1 will just give me this original series again. So n equals 0 to infinity of c sub n, n plus r, x to the n plus r minus 1. And then times the x would give me the sum of n equals 0 to infinity, c sub n, n plus r, x to the n plus r. This is where not having a big whiteboard is kind of difficult. I'm trying to squeeze all this in here. We still have this last series here. So let's say the sum of n equals 0 to infinity, c sub n, x to the n plus r. And this should equal 0. Now, normally the next step is to make all these powers k. Okay. We also talked about taking this r out. So let's look at the r first. We said, we could pull out an x to the r from this one. We could pull an x to the r and x to the r here. So I'm basically just going to say, let's drop that r, let's drop that r, let's drop that r, let's drop that r. That's because what we're really doing is factoring out an x to the r out of this whole thing and then getting rid of it. But rather than go through all that, from the last example, you kind of saw that happen. And then we would switch to k's, but let's not switch to k's yet. Look at the power on this, x to the n minus 1. This is x to the n minus 1. And they have the same exact starting index. We could put these two series together. Same thing goes for these two, x to the n, both start at 0. So I could condense these two series together. I can condense these two series together to make my life a little bit easier. So what would I get here? The first two would be n equals 0 to infinity. They're both going to be an x to the n minus 1. So then what would I have? I would have this coefficient plus this coefficient. Well, guess what? They both have a c to the sub n in them, so I could actually factor that out. They both have an n plus r in them, so I could factor that out. So then really what's left is 2 times this plus all this came out, so there's really a 1 there. So I would have 2 times n, 2 times r, oh you can't see that, 2 times n plus 2 times r minus 2 plus 1 would give me a minus 1. And again, where did that come from? 2 times this is all that was left here, and there was a 1 in front of this one, so plus the 1. So 2n, 2r, minus 2, plus 1. That's all what's here. I pulled out the n plus r in both of them, pulled out the c sub n in both of them, and there you go. I'm going to do the same thing over here with this other one. These two are going to come together. They both start at 0. They both have an x to the n. They both actually have a c sub n as well, so I'll pull that out. So then what's left? Well, what's left is I have an n plus r here. That's all that's left. Plus, since all this has already come out, there's a 1 sitting right here. So I could do n plus r plus 1. So the next thing to do is to go to k. In this case, k equals n minus 1. Here, k equals n. N would equal k plus 1. So I would get the sum of k equals negative 1 to infinity of 2 times k plus 1 plus 2r minus 1, k plus 1 plus r, c sub k plus 1, x to the k, plus the sum of k equals 0 to infinity of k plus r plus 1, c sub k, x to the k. And this together could give me 2k, 2 and the minus 1 would be 2r, and this would give me plus 1. That would be what this piece equals. Okay, so in this, we have to finish this off. We got to run one term out of here because this starts at negative 1, this starts at 0. So we'll plug k equals negative 1 in. We'll get negative 2 plus 2r plus 1. Then we're going to get negative 1 plus 1 plus r, c sub 0, x to the negative 1. Now the whole thing starts at 0. So I'll take this one plus this one starting at 0. So I'll have this coefficient, which is 2k plus 2r plus 1, k plus 1 plus r, c sub k plus 1, plus k plus 1 plus r, c sub k. And that whole thing is x to the k, and that should equal 0. Much like before, this coefficient has to equal 0, and all the other ones have to equal 0. So if this equals 0 here, we get 2r plus 1 times r c sub 0 has to equal 0. So again, this would equal 0 if r equals negative a half. This would equal 0 if r equaled 0, and this equaling 0 does nothing to help us. So we won't let that equal 0. This one over here would give me c sub k plus 1 equals negative k plus 1 plus r c sub k over 2k plus 2r plus 1 times k plus 1 plus r. Now, the k plus 1 plus r's can cancel, thus giving me c sub k plus 1 equals negative c sub k over 2k plus 2r plus 1. And remember, what k's are we using? 0, 1, 2, 3, because that's where k started. But again, this formula has two r's in it. Has r in it, sorry, and there are two different r values that we found. So we could say if r equaled 0, we would get c sub k plus 1 equals negative c sub k over 2k plus 1. And if r equaled negative 1/2, we would get c sub k plus 1 equals negative c sub k over 2k minus 2 plus 1. So that would give me, wait, there's a major mistake here before it messes me all up. Let me show you. This is actually going to give me 2r minus 1. There's a minus 2 and a plus 1. That would be a plus 1/2. That's a plus 1/2. So this is going to give me 2k plus, 1 plus another 1. 1/2 times 2 is 1, and another 1. So we would get negative c sub k over 2k plus 2. All right, so I caught that before it got too bad. But anyway, there's one, and there's another formula for c sub k plus 1 depending on r. So we'll run this one out, see what happens. We'll run this one out, see what happens. Both of them, we're working with k equals 0, 1, 2, 3, etc. Okay, for this first one, we let k equal 0. We get c sub 1 to be negative c sub 0 over 1. K equals 1. We get c sub 2 to be negative c sub 1 over 3. But based off of c sub 1, that's going to be c sub 0 over 3. K equals 2. We get c sub 3 to be negative c sub 2 over 5, which would then give me negative c sub 0 over 3 times 5. I think you see a pattern developing already, so we could say, all right, well, the solution was of the form y equals the sum of n equals 0 to infinity of c sub n x to the n plus r. In this case, with r equal to 0, we would get the sum of n equals 0 to infinity of c sub n x to the n, which would simply just be c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, etc. C sub 0, we're just going to let be c sub 0. We didn't want it to be 0 because if c sub 0 was 0, everything's 0. So it's just going to stay c sub 0. C sub 1 is going to be negative c sub 0. C sub 2 is going to be positive c sub 0 over 3. C sub 3 is going to be negative c sub 0 over 5, or 3 times 5. Then positive c sub 0 over 3 times 5 times 7 would probably be the next one. You can see that pattern, and it's just going to continue. So pull out a c sub 0, you get 1 minus x plus 1/3 x squared plus 1 over 3 times 5x cubed. I missed the minus there. This is a minus. Plus 1 over 3 times 5 times 7, x to the 4th minus, etc. But there you go. There's one power series solution. There's your y1. But we have another r value in another formula, so then we're going to get a y2. The other recurrence formula where r equal to half, I did have a little mistake there. Is c sub k plus 1 equals negative c sub k over 2k plus 2r plus 1 was the formula. And if r equals a half, that would actually give me negative c sub k over 2k plus 1 plus 1, which would be negative c sub k over 2k plus 2. Okay. Originally I just said 2k, but it's 2k plus 2. And that would be k equals 0, 1, 2, 3, etc. So anyway, with k equals 0, we would get c sub 1 equals negative c sub 0 over 2. K equals 1, we get c sub 1 equals negative c sub, or c sub 2 equals negative c sub 1 over 4. But that would actually give us positive c sub 0 over 2 times 4. K equals 2, give me c sub 3 equals negative c sub 2 over 6. But that's going to give me 6. C sub 0, negative c sub 0 over 2 times 4 times 6. So again, we said, well, the solution should be of the form n equals 0 to infinity of c sub n x to the n plus r. In this case, though, with r being a half, we would get the sum of n equals 0 to infinity of c sub n x to the n plus a half, which we could also write as the sum of n equals 0 to infinity of c sub n x to the n times x to the half. And again, x to the half is actually a constant multiple we could pull out. So we write this as x to the 1/2 times the sum of n equals 0 to infinity of c sub n x to the n. Ultimately writing this as x to the 1/2 times c sub 0 plus c sub 1x plus c sub 2x squared plus c sub 3x cubed, etc. And then going and saying, all right, well, that's x to the 1/2 times c sub 0 plus c sub 1 was negative c sub 0 over 2. And then c sub 2 was positive c sub 0 over 2 times 4. And then c sub 3 was negative c sub 0 over 2 times 4 times 6. And that pattern will just continue. If we then pull out a c sub 0, we're left with x to the 1/2 times 1 minus 1/2 x plus 1 over 2 times 4x squared minus 1 over 2 times 4 times 6 x cubed plus etc. So now that whole thing is actually our second solution. So even though Frobenius theorem says you're only guaranteed at least 1, we got 2 in either case. And that's going to happen a lot. Again, look at the r values. R was 0 and r was a half. The difference between them is not an integer. And so that's largely the time where we're going to get these two solutions. When the difference between them is an integer, it starts to get more complicated. And like I said, we're not going to get that far into singular solutions because we could always just deal with ordinary solutions if we really, really needed to. Anyway, so there's your examples for the solutions about a singular point. You see they basically work out the same way every time, for at least a couple of ones where the r values are difference between, that's not an integer.